Welcome to part 14 of the lecture on designing organic syntheses. In the preceding lesson, we discussed the synthesis and the retrosynthetic analysis of five-membered hetarenes. Today, we will start with an example for an annihilated five-membered heterene. And you will soon notice that our target molecule is an indole derivative. We have a pyronucleus here, benzoanilated, then it is indole. And with an additional six-membered ring, we call that a carbazole, and in that case, this would be a tetrahydrocarbazole. And again, of course, it is an indole derivative. So, retrosynthetic analysis. One suggestion should be disconnecting here. Then we would presumably choose to have the donator reactivity at this position. This is in accord with the natural reactivity here. We have the delta minus there. And acceptor reactivity here. Just let us put an X there as a leaving group. However, we of course know that just heating up and hoping for a nucleophilic substitution won't work, because nucleophilic substitution, well, is feasible at sp3 hybridized centers, not that easy here at an arene, especially not if it is an electron-rich arene, as in this case. Then the normal nucleophilic aromatic substitution with an addition-elimination mechanism doesn't work. There is another nucleophilic aromatic substitution with an elimination addition mechanism with arenes as reactive intermediates. And this is the case here that it works. It is reported. So, indeed, applying a superbase system, in this case sodium amide, in combination with sodium tertiary butoxide, well, a superbase, starting at low temperature and then heating it up. Well, this works, but in this case we have, as an intermediate, of course, deprotonated at the acidic NH group, sodium here, and then, as I said, elimination addition process, an elimination here, forming this arene. Highly reactive species there, nucleophilic center there, should give the CC connection Okay. And since this here is acidic alpha to the imine, it will be deprotonated here, this will be protonated, and then we have already the aromatic pyrrole moiety formed there, and the target molecule just by acidic hydrolysis. So, this is one possible retrosynthetic pathway. Let's have a look at another one, just disconnecting here. Well, by the way, I should add, one could think about using palladium catalysis for forming this CC bond. Well, it would just be a try using a palladium zero catalyst with an additional base, then an oxidative addition should occur into the CX bond. For X could be chloride, bromide, or iodide. Well, in this case, we should keep in mind also that we have an equilibrium here. Generally, the imine is preferred in the imine enamine tautomerism. Nevertheless, if we have this one or the imine, the base will deprotonate and we have the nucleophile, and well, hopefully HX is eliminated with under the influence of the base, and we would get this intermediary six-membered Pallada cycle, which easily should eliminate palladium zero, reductive elimination under CC bond formation. And after tautomerization, we would then get our target molecule. Well, okay, should work with the right, correct choice of the ligands, with appropriate ligands, it should work. However, I looked it up in SciFinder and couldn't find that published. Well, maybe one of you will have a try. Let's go to R2. This disconnection would lead us to an aniline with this cyclohexanone moiety in ortho position. Well, actually, we just need nucleophilic nitrogen here and here just two leaving groups. Could be a ketone or it could be an imine. And this is especially interesting since we could then draw the tautomer, which is of course unstable, but rather interesting, since, well, you already notice where we will get to. To this system capable to undergo a diazer cope rearrangement. And we all know under acidic treatment, heating it up, this works, directly tautomerizes to this one and eliminates NH3, delivering the target molecule. And well, this is then the preferred synthesis of our target molecule, just starting with phenylhydrazine plus cyclohexanone. First, under acidic conditions, for instance in ethanol, forming the hydrazone, and then secondly, heating it up. This is sufficient for producing that target in rather satisfying yields. And as you know, this is called the Fischer-Indole synthesis. Let's have a look at the synthesis of 6-membered nitrogen hetarenes, for instance pyridines. Certainly the most important class of heterocycles, of nitrogen heterocycles. R should be just any substituent, alkyl or aryl. E should be an ester. Let's choose just an ethyl ester. So we have an imine functionality on this side, an enamine functionality on the other side. So, straightforward disconnection means that we could get to this structure, for sure, using something like that and treating it with just ammonium acetate will deliver the pyridine derivative. We could try to disconnect here. Okay, we will have a look at a similar case. This is then the preferred disconnection. However, if you think of getting rid of that double bond here, then we have a highly symmetrical setup, and in the ongoing retrosynthetic analysis, we could just assume we have here donator reactivity, there donator reactivity. This is, of course, the natural reactivity of acetoacetic acid ester, just deprotonating there, or also forming the enol under acidic conditions. On the other hand, we need a carbon with double acceptor reactivity, and as you all know, the synthetic equivalent of something like that is simply an aldehyde. So +2 equivalents of acetoacetic acid ester. And indeed, if we put those reagents together with ammonium acetate, then we can nicely produce a dihydropyridine usually the 1,4 isomer, and then oxidizing for oxidizing it, you could use, for instance, iron chloride or these oxidizing agents like DDQ, or maybe just oxygen, air, plus a catalyst. For instance, this one with R is just a hydrogen. That means that aqueous formaldehyde was applied. Then this product was reported as isolated with a 93% yield. This type of pyridine synthesis is known as the Hunch pyridine synthesis, which can be stopped at the stage of the dihydropyridine. Then it's of course the Hunch dihydropyridine synthesis. Similarly, you can analyze the synthesis or retrosynthetic analysis. You can analyze the potential synthesis of this target molecule. And now, in this case, it's obvious that it could be a good idea to disconnect here. Getting to this pentane dione and acetoacetic acid ester. So again, just treating with ammonium acetate will be sufficient to get that, well, 3-component coupling process, condensation process done to get to the pyridine. As an alternative to this diketone, one could also choose this alkynone. So then the nucleophile would attack here in, well, as a Michael addition process. Finally, with the same result, of course. Now to annihilated systems. Benzoanilated pyridines are called quinolines or isoquinolines if the nitrogen is at the 2 position. Let's analyze this target. Disconnecting here. So, this alpha-beta unsaturated ketone certainly derives from a condensation process of that ketone with acetone. Well, actually, if we put those together, I would assume that, first of all, a condensation process will take place between the aniline and the acetone. Imine, enamine, tautomere. Now here we have the nucleophile, there we have the electrophile. Well, standard mechanism protonation here, deprotonation there, elimination of water, gives our target molecule. So, one problem which should be solved is, how could we synthesize something like that? Well, in literature you will find two ways for getting to structures like that. One is having a nitro compound and selectively reducing that. Well, I'm a bit surprised that it should be that easy to introduce that selectively alpha to a CH acidic compound and then selectively reduce that without reducing the carbonyl group, but it seems to be the preferred method. However, there is this nice way for a transformation. Start with the aniline, acylation, and then a rearrangement. This is then the so-called one example of a freeze rearrangement. It is possible with carboxylic acid amides. The normal freeze rearrangement is with an ester, with a phenol ester, but it works with amides. Just treating that with a Lewis acid like zinc chloride, and it will go to the ortho position if you have blocked the para position. Without blocking the para position, then normally you get a mixture. And there is also the possibility to accelerate this reaction photochemically, and then it's the photo-freeze rearrangement. So, photo-freeze rearrangement in brackets. So, next subject, let's have a look at isoquinolines. And as an exercise, you already thought about structures like that. Well, okay. Most of you decided to disconnect here. Certainly not a bad idea. Well, you have the problem with this cis-trans isomers. Well, however, chances are not that bad that under the influence of a Bronsted acid you get the isomerization done, and as soon as this cis structure occurs, it will react and give the cyclization. Well, targeting this structure, we could think of disconnecting here R1 just an idea. How could we get such a setup? Well, also just a spontaneous idea. One moment, we have an R group here. So, okay. Ozonolysis of an indene derivative. Well, why not? Maybe because we would now have to think about how we synthesize this one. Yeah? Okay. And on the other hand, some of you suggested that we could change oxidation state well, ending up at the structure with an aldehyde and a keto functionality in ortho position. Well, I'm not sure. Going on in that analysis, one could think about, do we have a way to well, get the transformation done from here to this one? Let's see. maybe we could reduce that carboxylic anhydride with a complex hydride which delivers just stoichiometrically one hydride. So diisobutyl aluminum hydride could be a reagent of choice. So first diisobutyl aluminum hydride, then secondly trapping with TMS chloride. Would give this lactone, and then maybe with just a Grignard reagent well, okay. Hydrolysis should give this one, just call it B whatsoever. Yeah. Yes, one could try that. Nevertheless, let us have a look at alternatives. As it will turn out, especially nice is thinking about a disconnection here. You will see that we will then soon get to, well, classical isoquinoline syntheses. Here, donator reactivity, there we acceptor reactivity. In this case, we have the special problem, the serious problem, that we would have to deal with cis-trans isomers. And since this is not conjugated to any carbonyl group. Here in the case we discussed before, we had the carbonyl group at least in conjugation through that phenylene moiety. But here, well, we can assume that indeed preferentially we would have a trans isomer with not an appropriate tendency for isomerization. So, and this connection here, well, it looks like an intramolecular Friedel-Crafts reaction. With a leaving group here, best would be a chloride. So, again, we have the problem cis-trans isomers. Well, we should therefore consider that we skip that double bond there. Then no problem with cis-trans isomerization. If we just have CH2, CH2, we will have to do an oxidation step within our synthesis, or we add retrosynthetically water to the double bond. That means in the synthesis we just have to eliminate water. So, where do we get such an imidoyl chloride from? Well, simply from the corresponding carboxylic acid amide, treating that with phosphor oxychloride. And the same here, of course, for this case. So, and obviously, you get these amides from the reaction of the free amine with, for instance, the acid chlorides. Treating this with phosphor oxychloride or that with phosphor oxychloride, it goes all the way to our target molecule, and starting from such an hydroxyamine, then the isoquinoline synthesis is called the Pictet-Gams isoquinoline synthesis. Having just the amine and including one oxidizing step, well, actually, the oxidizing step is the one on the stage of the dihydro isoquinoline. Okay? So, but nevertheless, this is called the Bischle-Napieralski isoquinoline synthesis. Now imagine that we change the oxidation state at that carbon. We could do so in our retrosynthetic analysis. Changing the oxidation state to this compound, well, which obviously is the product of the condensation reaction with an aldehyde. Then this intermediary imine, just treating that under acidic conditions, will deliver this tetrahydro isoquinoline. And indeed, this reaction producing a tetrahydro isoquinoline with stereogenic center usually here is a biomimetic one. There are lots of natural products with that structure, and also in living systems. This reaction occurs. Condensation of such an amine with an aldehyde and under acidic catalysis, we get to the tetrahydro isoquinolines. This is a synthesis following Pictet-Spengler. And of course, you could then oxidize under more vigorous conditions to get to the aromatic isoquinoline. While oxidizing under more vigorous conditions, one should pay attention that you don't oxidize that nitrogen to the N oxide. This is, of course, possible with peroxides, hydrogen peroxide, for instance. One last example for an isoquinoline synthesis, which is also used for the synthesis of a parent isoquinoline, but we will just have a look at this example with an additional hydroxyl group, this phenolic isoquinoline. You could disconnect here. So, imine functionality, the cyclization is also of Friedel-Crafts type. So, you would then start from this aldehyde and this amine with that acetal functionality which you can buy. Combining these under slightly acidic conditions from 0 degrees to room temperature, 48 hours, and 46% yield is reported. This is a nice example for the so-called Pomeranz fridge isoquinoline and synthesis. So, I think enough for today. Thanks for listening. See you tomorrow.